Unit operation classroom. In this problem, we are discussing coefficient of contraction from vena contracta diameter. My name is Shekhar Bhattacharjee. Water is discharged from vertical side of a tank through a circular orifice of diameter 2 centimeter under laminar flow conditions. So let's say this is my vertical tank, and here's a little hole. Let's call this as an orifice, and the water gushes out from this orifice right here. And we maintain a constant level here. The water surface in the tank is maintained at a constant level above the center of the orifice. So because of the static head, there will be a continuous flow of water from this orifice. And what happens? Streamlines converge. The streamlines converge at this vena contracta. We know that, right? So this is the orifice diameter, and right here this is the vena contracta diameter. Okay. So we have to find these values are given. This is 2 centimeter and this is 1.6 centimeter. We have to find out the coefficient of contraction. This is a very easy problem as long as we know what is the definition of the coefficient of contraction. So this is the area of jet at the vena contracta right here divided by the area of the orifice. So this part, of course, is easy. So this is the ratio of the square of the diameters, and that is equal to 0.64. So what does it mean? That the actual area of the vena contracta is 64%. Actually, the vena contracta is 64% of the orifice area. So, although this is 2 centimeter, the diameter of the orifice, effective jet diameter is 1.6 centimeter, which we have is already given in the problem. Okay. So, so as you can see, this is a very easy problem. What is the process industry relevance of this problem? Let's say is a reactor draining, liquid phase reaction, and there's a liquid transfer. So we know that through the orifice, this is the theoretical from which we get from Bernoulli's equation, but the Q actually have to multiply by the discharge coefficient, which is the product of the coefficient of contraction multiplied by the coefficient of the velocity. This is little difficult to determine, even if we assume this is equal to 1. So this CD you can take this is equal to coefficient of contraction, right? So that's around 0.64 for orifice. We know. Similarly, for orifice flow meters, we just multiply the theoretical one, which is this one right here, with the discharge coefficient CD, which is this one right here. So, as we say, for finding out the actual flow rate, you have to know this is either by the actual the contraction, and you have to take this diameter if this is the configuration to calculate the flow rate out of this orifice. So you have to take this particular diameter. Answer is, of course, 0.64.